Welcome to my IGCSE Edexcel all-in-one chemistry video. This is for the 9:1 new specification. Now, as always, don't forget that I sell my perfect answer revision guides on my website, which is www.sciencewithhazel.co.uk. If you click on this card, you'll be able to go and purchase yourself a copy. It is available now in all 3 sciences. So if you enjoy my videos and you enjoy the way in which I describe and explain things, that is where you will find a distillation of my videos. You'll also find information about revision courses if you're keen on attending, school licenses and private tuition. However, enough about that, let's get started. So we're going to start by looking at solids, liquids and gases. So when we look at solids, liquids and gases, be prepared to draw their particle diagrams. Notice that solids have particles which are in very fixed arrangements, and that's because the particles vibrate around in fixed positions, they have little kinetic energy and there are strong forces between them. Moving to liquids, you see that the particles are slightly more widely spaced apart. They're not touching quite as much, so they have intermediate forces between them and they vibrate more and they don't have fixed positions. Gases now, so you need your particles to be further apart. This is because they have large amounts of kinetic energy. Obviously they're not held in fixed position and there are weak forces between the particles, and here's your summary now. Let's start naming the correct conversions between all these various states of matter. So remember, if you're going from a solid to a liquid, that is melting, like a solid ice block turns into water, melting. If you go the other way and the water turns into ice, clearly that will be freezing. If you have a liquid and it turns into a gas, that will be boiling or evaporating. And then when you have a gas and it turns back into a liquid, that is condensation. So that's what happens when you have a shower and you see it getting all misted up on the windows. Condensation is occurring here. Touching slightly more on evaporation, so how does the evaporation of a puddle or any liquid happen really? So what you find is that the particles have differing kinetic energy. Now those particles with the most amount of energy will evaporate first and they will leave the surface of the liquid. And what will happen is it will mean that the remaining particles have lower average kinetic energy. Do notice that in a closed container, condensation and evaporation will be occurring simultaneously, which means at the same time. The specification now touches on diffusion, which you should be aware from biology. So diffusion is the net movement of particles from an area of high concentration to an area of low concentration. And because that's down the concentration gradient, you find that no energy is required. It is a passive process. So that means in any scenario where you have a large amount of particles in one place, they will drift and move across to somewhere, some region which has a lower density or concentration of these particles. And the example we like to look at in chemistry is, you might have seen your teacher go through it in class. You've got this huge glass tube, and one end you have ammonia, the other end you have hydrochloric acid, and effectively their concentrations are high at either end of the tube, and obviously the particles start to diffuse. So the ammonia starts to move towards the hydrochloric acid, and where they meet, a chemical reaction takes place and ammonium chloride is produced, which we see as a white ring. Now, the location at which this white ring occurs will tell you something about how quickly diffusion is happening, because clearly if the white ring occurs in the middle of the tube, it means that the ammonia and the hydrochloric acid diffuse equally quickly across. However, this isn't true. What actually happens is that the ring forms much closer to the hydrochloric end. And that means that the ammonia has diffused further and faster. And what is the reason for this? It's simply because it has a lower relative atomic mass. Looking at solutions now, so be aware of the solution words you need to know and their definitions. So we're going to use coffee being dissolved in hot water as our example so that you can actually understand the words I'm saying. So we're trying to make a nice cup of coffee and we're going to start by looking at what a solute is. So a solute is a solid which dissolves in a solvent. So in the case of our coffee example, the solute is the coffee grounds. The solvent is the liquid in which the solute dissolves. So in our example, that would be the hot water. The solution is the mixture of the solvent and solute. So that would be the nice cup of coffee that we make. And then a saturated solution is one where you can't dissolve any more solute into the solvent. So it's at its maximum capacity effectively. Looking at some fundamentals which underpin chemistry, we need to look at an atom, element, mixture and compound. So an atom is the smallest particle of a substance that can exist. There are probably more accurate definitions for this, and that will involve high level physics, but for all intents and purposes for your chemistry GCSE, this is what you need to know. An element contains only one type of atom and it cannot be split by any chemical means. So basically, if you're given a list of substances and you're asked which is the element, cross-reference the list to the periodic table and you'll soon be able to see if what you have is an element or not. If it's not in the periodic table, it is not an element. Compounds now, well, that's when you have two or more elements which are chemically combined, and what that means is you cannot separate them back into their constituent elements. And a good analogy for this is when you make a cake. So you add flour, eggs, sugar, and effectively when you bake it, it turns into a cake, and that's the equivalent of a compound because there's no way you can separate those cake particles back up into eggs, flour, sugar. That's not going to happen, and that's due to the chemical reaction that's taken place. A mixture is different to this. A mixture contains, as you would imagine, two or more elements, this time not chemically combined, so theoretically you should be able to separate your mixture into its constituent components. And now I'm just going to bring up an example table showing elements, compounds and mixtures, and you should have a go at potentially separating them out yourself and make sure you can tell the difference. When we look at a pure substance, this is a substance which contains only one type of material. So that could be, for example, one element, so carbon, or it could be one compound, such as carbon dioxide. But the point is there's nothing else in there contaminating it. If you think you have a pure substance and you want to look at its boiling point, be aware that a pure substance will have a fixed boiling point and should not boil over a range of temperatures. If it boils over a range of temperatures, as crude oil would, it's a mixture, it is not a pure substance. We now need to touch on separation techniques, so I'm going to give you all the different examples and how you would use each of them. So first of all, filtration. You are going to use this to separate an insoluble solute from a solvent, and your example here could be sand and water. The reason filtration works so well is you pour the mixture through the filter funnel containing filter paper, and what you'll find is the sand stays in the funnel, the water flows through into the beaker below, so you've separated your insoluble solute from the solvent. And be prepared to label all the apparatus involved and be able to draw simple diagrams. Getting slightly more complicated now, we now have a soluble solute that needs separating from a solvent. This could be something like salt being separated from water. So clearly filtration won't work because the salt will go straight through into the beaker below, which is why we need to use evaporation. So you have a tripod with gauze on the top, an evaporating basin containing the salt solution. You boil using a Bunsen burner. The excess water boils off and you're left behind with salt in the evaporating basin. Next up, we're separating immiscible liquids. So these are liquids which do not mix. A good example here is oil and water. And you will find that oil, and you can see this at petrol stations, if for some reason it's rained and then petrol's ended up in the puddle, you can see the petrol floating on top of the water, and that's what happens with oil too. So in this case, you can just put it into a funnel, you can open a tap and the water will drain out first, close the tap and you'll leave the oil behind in the funnel. Now liquids of different boiling points, for example ethanol and water. Clearly evaporation and filtration won't work here, and this is where you use simple distillation, and simple distillation relies on the fact that liquids have different boiling points, because what happens is you use a Bunsen burner to boil the mixture of liquids, and the liquid with the lower boiling point will evaporate first. So that would be the ethanol with a boiling point of 78 degrees Celsius, leaving behind the water below. And if you have a real mixture of liquids with lots of different boiling points, such as crude oil, this is where you'll use fractional distillation, which actually allows you to separate out many different liquids of different boiling points. Our last separation technique is chromatography. Remember, this is used to separate liquids of different solubilities, so that could be food colouring, dyes, inks, for example. Be prepared to describe how you set up a chromatogram. Remember, you have filter paper, which you draw a reference line on in pencil. You put the dots of ink along the pencil line, and then you dip the paper into water. As the water soaks up, it draws the dyes up the paper, and you can determine several things from that. So first of all, notice that you draw the reference line in pencil. Why? Because you don't want the pencil to spread and go flowing up the paper too, because that will disrupt your chromatogram. Notice that the ink which travels the furthest has the highest solubility, which kind of makes sense. And be prepared to use the formula, which is the RF formula. And that's the formula whereby the distance travelled by the component is divided by the distance travelled by the solvent. Back to basic chemistry then, so we're looking at periodicity. I've already told you that an atom is the smallest part of a chemical element which can exist. So what is a molecule? Well, that is two or more atoms bonded together, and the atoms could be the same element, such as H2, so hydrogen, or it could be different elements such as carbon dioxide, but the point to notice is that with a molecule, it's just two atoms stuck together. So looking at the structure of an atom, remember that we have the nucleus in the middle, that contains the protons and the neutrons. Surrounding that we have circles which we call shells, and these are shells of electrons. Do remember when you're drawing electronic configuration diagrams that the first shell can contain a maximum of 2 electrons, and after that you can contain a maximum of 8. So let's compare the masses and charges of protons, neutrons and electrons. So protons and neutrons both have a mass of 1. So they're much heavier than electrons, and that's why we say most of the mass is found in the nucleus of an atom. An electron has a much smaller mass, and different examples will say different things, but I tend to say that it has a mass of 1 divided by 2000, so a very small number indeed. Looking at the charges now, neutron, so neutral, has no charge because it is neutral. A proton, positive, has a positive 1 charge, and an electron has a -1 charge. So when we look at an atom, we know that it is uncharged, which therefore means it must have equal numbers of electrons and protons. When we look at the periodic table, you must be really familiar with how to use the periodic table and what it's telling you. So make sure you use the key, because that will tell you which is the mass number and which is the atomic number. But generally speaking, the top number tends to be the mass number and the bottom number tends to be the atomic number. So the atomic number is actually the number of protons found in an atom. So for carbon, that would be 6. And I told you already that atoms are neutral, which means their proton number equals their electron number, which means the electron number of carbon will also be 6. And if we draw the electronic configuration diagram, we know that 2 electrons go into the first shell and the remaining 4 go into the second shell. Now looking at the mass number, now the mass number is the total number of protons and neutrons. So if carbon has an atomic number of 6, that means the proton number is 6, it has a mass number of 12, that means you can work out the neutron number by taking the atomic number away from the mass number, so the neutron number of carbon is 6. Small thing to notice is the nucleon number, and that's just the total number of particles found within the nucleus of an atom. So it's the total of the protons and neutrons, i.e. it's also the mass number, so they're very closely linked. Isotopes now, so if you look in the periodic table you will see that some mass numbers aren't whole numbers, such as chlorine, which is 35.5, and that's because chlorine exists as an isotope, which means that some chlorine atoms have a high mass number of 37 and other ones have a mass number of 35, and when you work out an average you actually find that it's 35.5, and that's because there are far more chlorine 35s compared with chlorine 37s. However, you just need to know the definition of an isotope, which is that it is atoms of the same element with the same number of protons but different number of neutrons. You may be asked to calculate the relative abundance of various isotopes, and now I will show you how to do that on the iPad. Now we need to touch on calculating the relative atomic abundance of these various isotopes, and this is how you need to do it. So the question will look something like this. The abundance of chlorine 35 is 75% and the abundance of chlorine 37 is 25%. Calculate the relative atomic mass of chlorine. So 35 is one isotope's mass and 37 is the second isotope's mass. So all you have to do is take each isotope's mass, so 35, times it by its percentage, which is 75, and add it to the second isotope's mass, times it by its percentage, and then divide the whole thing by 100. And when you do that, you get the answer of 35.5 to 3 significant figures. And that's how you need to do it. Doesn't matter what the element is,
you times its mass by its percentage, add it to the other mass, times it by its percentage, and divide by 100.
Relative atomic mass I've already described a little bit, but you do need to be able to define it, and that is that it's the ratio of the average mass of an element when compared with one atom of carbon-12. Going back to the periodic table then, looking at group numbers and period numbers. So the group numbers are the numbers that run along the top of the periodic table. The group number corresponds to the number of electrons in the outer shell. So group 1 elements will all have 1 electron in their outer shell. Now the period numbers run down the side and they refer to the rows, and the period number will correspond to the number of shells of electrons. Why do elements in the same group tend to have the same chemical properties? That's due to the number of electrons in the outer shell. So the answer here is because they have the same number of electrons in the outer shell. So why do fluorine and chlorine behave similarly? Because they're both in group 7 and therefore they both have 7 electrons in their outer shell. Let's look at group 0 now. What is their name otherwise known as? It is the noble gases. And why are they so unreactive? And that's because they have full outer shells, which means they don't really want to get involved in bonding. As a quick overview of the periodic table, do notice there's a step line on the right hand side, and therefore the metals occur on the left hand side of that step line, and the non-metals appear on the right hand side, with hydrogen appearing by itself at the top because it behaves very differently from all other elements. So metals now, we're going to start by looking at their properties. So remember, metals have high melting and boiling points, they're good conductors of heat and electricity, they are shiny, they are sonorous, which means when you hit it they make a noise, they are malleable and ductile. So what does malleable and ductile mean? Well, malleable means that they can be hammered into shape, and ductile means they can be drawn into a wire. Another thing to notice is stuff relating to how they bond. So be aware that when they enter into bonding, they tend to lose electrons to become positive ions. They form basic oxides, which we'll come into later, and they partake in ionic bonding. Non-metals now, their properties include the following. They are dull, so they're not shiny. They tend to have low boiling and melting points. There are exceptions to this, which we'll come on to later, but that is the general rule. They are brittle, which means when you hit them they easily break. They form acidic oxides. They gain electrons in bonding to become negative ions, and they partake in covalent and ionic bonding. So how is an ion formed and what is an ion? So an ion is a charged particle which is formed from either gaining or losing electrons. So clearly if they lose electrons, they lose negative charge, so therefore they become positive. If they gain electrons, they gain negative charge, so they become negative.
I'm going to show you my favourite method of balancing equation, which always works. So if you can't actually see straight away how to balance them, use this method and you'll be able to balance any equation. So start by doing a dotted line and then list the elements present on each side of the equation, and obviously they ought to be the same. So we've got hydrogen, nitrogen, oxygen, calcium, and then just copy that straight over and line it up nicely. And now we want to do a tally chart to show how many of each element we have. So count the hydrogens on the left hand side of the equation. So we've got 1 present in the nitric acid, 2 present in the calcium hydroxide, so that's 3. The number of nitrogens is 1. The number of oxygens, well, 3 on the nitric acid side, and then you've got 1 inside the brackets, but the 2 after the brackets means that there's 2, so add those up all together and it's 5. And now the calciums is just 1. Now we need to do the same for the product side of the equation. So how many hydrogens do we have? Well, that's 2, which is present in water. Oxygen, you've got 3 present in calcium nitrate, but remember that small 2 after the brackets means that's doubled, so that's 6, plus 1 found in water, so that's 7. Nitrogen, you've got 2. In calcium you have 1, and now we need to have a look at our tally charts and see what the issue is. So the calcium are fine, the nitrogen are not fine. You've got 2 on the right hand side, 1 on the left hand side, so we're going to add a big 2 in front of nitric acid. Remember, when we're balancing equations, all you're allowed to do is add big numbers. And now readjust your tally. So you now have 4 hydrogens, 8 oxygens, 2 nitrogens. So the nitrogens are happy, the calcium is happy, but the oxygen hydrogens aren't, so I'm going to put a 2 in front of water to make that 4 hydrogens. And now adjust the oxygens, so you now have 8 oxygens. And look, the whole thing is balanced because you have 4 hydrogens on both sides, 2 nitrogens, 8 oxygens, and 1 calcium, so that is indeed balanced. Looking at more calculations now, use the formula triangle to help you rearrange, and you can see that mass is therefore given by the relative atomic mass, which is mR, times number of moles. Moles is going to be mass over mR, and that's a good way of rearranging without too much effort. So let's get started and have a look at some examples. So first of all, we're just finding the mR of calcium hydroxide, and that's just a matter of looking up the various masses in the periodic table, tends to the top number and adding them all together. So if we have a look, we see calcium is 40, oxygen is 16, but we have to times it by 2 due to this small 2 here, and then we add hydrogen, which is 1, and again times it by 2. Pop that into your calculator, and you get an mR of 74 grams. Now looking to find the number of moles in 5.4 grams of calcium carbonate. So I like to write out the equation I'm using, it's good practice. Stops you making silly mistakes. So using my formula triangle, I see it's mass divided by mR. We've been given the mass in the question, which is 5.4. Now we need to work out the mR of calcium carbonate. So using the periodic table, calcium has a mass of 40, carbon is 12, oxygen is 16, and we need to multiply that by 3 due to this 3 here. So that's 5.4 divided by 100 of 0.054. Now we're looking to find the empirical formula of a compound which contained 22% carbon, 4.6% hydrogen and 73.4% bromine. I like to lay out these questions always using the table format. So first of all, list your 3 elements and then draw a table underneath. Mass, mR, moles, and don't forget your formula triangle. Always be aware. So remember, mass is at the top, mR and moles. And then just substitute what you know from the equation, from the question. Now notice, even though it's given percentages, because it's a ratio, really you can ignore the percentages and pretend that those are the masses, which is why I'm now going to put the mass of carbon as being 22, hydrogen is 4.6 and bromine is 73.4. Now use your periodic table to find their MRs. Carbon is 12, hydrogen is 1 and bromine is 79. And then looking at our formula triangle, we see to calculate the moles, we simply do mass divided by MR. So that's 22 divided by 12 for carbon, which is 1.83 recurring. 4.6 divided by 1 is obviously 4.6. And then 73.4 divided by 79 is 0.929113. And a note here, don't round too early because the numbers are so small, you'll introduce rounding errors. Keep them nice and long in your calculator. Then we want to divide by the smallest number. So just have a scan, and obviously 0.9 is the smallest number, so we're going to divide all of the previous answers by that number. And this is so that we have a ratio. I wish my iPad would stop deleting stuff, but it doesn't really make that much of a difference. So once you've done that, you know that will be 1. This comes out of 4.95, which I can happily round to 5 because that's basically what that number is. And this comes out of 1.98, so that's basically 2. So don't be scared to round, only if the numbers are very close. If one of the numbers had come out at 1.5, for example, so for example 1.5 versus 1, what you'd have to do in that case is double both, so you have a ratio which is 3:2. But I don't want to talk about that now because I want to finish this question. So don't forget to actually provide your empirical formula, which is C2H5Br. And that is your final answer. Sometimes they like to extend the question and tell you in part B that a different compound had a mass of 216, and then based on this empirical formula you've just calculated, work out its molecular formula. This is really straightforward. All you have to do is work out the MR of the empirical formula you've just calculated. So work that out, which would be 2 times 12 plus 5 times 1 plus 79. So that's just a basic MR calculation. Once you've done that, you see that it's 108. And compare it to the compound you've been given, which is 216. So the compound you've been given must therefore have a molecular formula which is just twice that of the empirical formula. So the actual final answer here is just C4H10Br2. If the MR of your empirical formula had been the same number, which is 216, then your answer would just have been the empirical formula, which is C2H5Br. Now I'm going to show you a water crystallization type of mole calculation. It's really similar to empirical formulae, so don't let it freak you out just because it looks more difficult. So 35.75 grams of sodium carbonate combined with water are heated strongly, and 13.25 grams remain after heating. Calculate X. So obviously after you've heated it, it will now become anhydrous, which means you've driven off the water. So lay it out like the table again, Na2CO3, but instead of listing the elements, you're just going to have the various components of the question. So it's just going to be sodium carbonate on the left, water on the right, and then mass, MR, and moles as usual. So we know that 13.25 grams of the sodium carbonate remain after heating, which is why this is the number here. Going to have to do a small calculation to work out the amount of water that was lost. So that's 35.75 minus 13.25 to get 22.5. The MR, use the periodic table, so we'll see sodium is 23, times it by 2 because of that small 2, plus carbon's 12, plus 3 lots of oxygen, which is 16, to get an MR of 106. And I know off by heart that the MR of water is 18, and you can check that in the periodic table if you don't believe me. To work out the number of moles now, mass divided by MR, giving us 0.125. This is 1.25. And then divide by the smallest number, which is clearly 0.125. So that will obviously be 1. This is 10. Therefore, X equals 10, and that's it. It's very similar to the empirical formulae question. Now we need to look at reacting mass and gas volume questions. So 3.3 grams of hydrochloric acid react with sodium carbonate. Calculate the mass and volume of carbon dioxide collected. Now, I do imagine that in your question paper they'll give you the balanced symbol equation, which is the starting point of this calculation. However, in another part of the exam paper, they could easily expect you to write out your own salt equations and to balance them, which is why I'm going to do all of that right now. So, hydrochloric acid reacts with sodium carbonate to produce a salt, which is sodium chloride, plus water, plus carbon dioxide. Make sure it's balanced. I know I need a 2 there and a 2 here. And now we need to use the table format in order to help us answer the rest of the question. So mass, MR, and moles. And don't forget to use your formula triangle down here, which is mass, MR, moles. And this is how I always set myself up to make sure I'm going to get the question right. So what have we been given in the question? Well, we know 3.3 grams of hydrochloric acid reacted, and we know we need the volume and mass of carbon dioxide, which is why my X goes here. Now the MR, use the periodic table. Now make sure you're just adding up the hydrogen and the chlorine. You're not including the 2 in this. So it's just 1 plus 35.5 equals 36.5 grams. The MR of carbon dioxide is going to be 12 plus 2 lots of 16, which is 44. Using the formula triangle, we see that moles is mass divided by MR. So we do 3.3 divided by 36.5 to give us 0.0904109. And now remember, what we can do here is carry that number across to be the number of moles of carbon dioxide. Do check the big numbers up here. Now there's 2 lots of hydrochloric acid compared with only 1 lot of carbon dioxide, which is why in order to carry over the moles we have to actually divide 0.09041 by 2, and that becomes 0.045205. And now we're ready to work out the unknown mass of carbon dioxide, which is mass equals mR times moles. We've already calculated the mR, which is 44. Moles is 0.045205. And that is 2 grams to 3 significant figures. 3.2 grams of copper reacted with 0.44 moles of nitric acid. Which reagent is in excess? Don't worry too much about this. We're going to use the same method as always, which is the table format. So we're going to write mass, mR and moles down the left hand side, and remember our triangle, which I'll put here, which is mass at the top, number of moles and mR. So we know that 3.2 grams of copper reacted, and weirdly we're going to put X here because that is important, and I'll say why soon. So first of all, what is the mR of copper? Using your periodic table you see it's 63.5. So using your formula triangle, how do you work out the number of moles? You do mass divided by mR, so that's 3.2 divided by 63.5 to get 0.05 mole. And then have a look at the big numbers. We've got an invisible 1 here, we have a 4 here, and I've already taught you, you just need to pull that number across, but instead times it by 4, so you get 0.2 moles. So now we compare, we have a look, and we have a look at what we were given in the question. Well, we were told we had 0.4 moles of nitric acid, but we only need 0.2, so clearly nitric acid is in excess. Now we're looking at percentage yields. So for example, in a reaction 11.2 grams of copper sulfate was obtained when theoretically 12.5 should have been obtained. Calculate the percentage yield. So you just need to use this equation here, which is percentage yield equals actual yield over theoretical yield times 100. So the actual yield here was 11.2, the theoretical one was 12.5, multiply it by 100, and you get a value which is 89.6%. Now they can be more difficult than this, so I'm going to show you that example now. So let me talk you through a slightly more complicated version. So a student reacted 2.4 grams of copper oxide with sulfuric acid. She made 1.8 grams of copper sulfate. Calculate the percentage yield. So as always, we need to start with a balanced symbol equation. So that will be copper oxide plus sulfuric acid, which is H2SO4, forms copper sulfate, CuSO4, plus water. And then step back and double check that it is balanced, and it is. And we're going to use my favourite table as well, obviously, because I never do a mole calculation without it. So let's start with what we know. We know that we have 2.4 grams of copper oxide, and we have made 1.8. So that is the actual yield, and we need to find out the theoretical yield, which is why I'm going to put an X here. So now it's just a matter of working out the mR of copper oxide. So do 63.5 plus 16, so use your periodic table for that to work out that its mR is 79.5. To work out the number of moles, simply do the mass divided by the mR, so that's 2.4 divided by 79.5 to give a value which is 0.0302 moles. Now we need to look at the balanced symbol equation and have a look if there are any big numbers. There aren't, so we can easily just carry that number across to be the number of moles of copper sulfate. Now work out the mR of copper sulfate, so you want to do 63.5 plus 32 plus 4 times 16. So that gives us an mR which is 159.5, and then we work out X by doing 159.5 times by 0.0302 to get 4.8169 grams. And now we can just substitute that into our percentage yield equation because that is the theoretical yield. So percentage yield is given by actual yield over theoretical times by 100 because we're looking for a percent. So actual was 1.8, theoretical was 4.8169, times that by 100, and we get a value which is 37%. Unfortunately, there are some ions which you'll simply have to learn off by heart because you can't work them out from the periodic table. So let's just go through what all of these are. Starting with these transition metals along here, just going to have to learn them. The first one is silver, this one is copper, Pb2 plus is lead, and zinc is Zn2 plus. Notice with transition metals like iron that have variable valencies, you'll be given it in the question so you can actually see what their charge will be given by the Roman numerals. So that's not something you need to remember. This is the ammonium ion. And now looking at the negative ions, if it's combined with oxygen, it tends to have 8 in its name. So this is carbonate, sulfate, and nitrate. And that final ion is hydroxide. So now we can get started on some examples. So starting with magnesium chloride, so let's write down the ions. We can see from the periodic table that magnesium is in group 2, hence Mg2+. Chlorine is in group 7, so 8 minus 7 is 1, hence Cl-. Now have a look, they're not balanced obviously. You've got a 2+ and a 1- charge, so clearly you need 2 chlorines. Remember when you're writing the formula, you write a small number after the element in question, which is why this is the formula of magnesium chloride. So lead hydroxide, these are both ions you're going to have to learn off by heart. So Pb2+, OH-. So we've got the same issue here in that we don't have enough minus, so you need 2 OHs. So you're going to write PbOH2. However, the 2 applies to both the oxygen and the hydrogen, which is why you need brackets. So insert brackets, and that is your formula. Now lithium. Lithium is in group 1, so it has an Li1+ charge. So it has a 1+ charge. Oxygen is in group 6. 8 minus 6 is 2, so it's O2-. This means you need 2 lithium for every oxygen, so Li2O. Magnesium nitrate. Magnesium is in group 2, so Mg2+. Nitrate you've got to learn from the list above, NO3-. You've got a 1- charge with nitrate compared with the 2+ charge on the magnesium, which explains why you need 2 lots of that nitrate, and you need to insert brackets again. Don't touch this 3 here, that just remains part of the formula. People get confused and start moving it around. No, that is the final answer. Lastly, aluminium in group 3, 3+. Learn sulfate's charge, which is SO4 2-. This is a difficult one now. It's not that clear. You've got to find a common number that both 3 and 2 go into, which is 6. So if I show you my thought process, I effectively need 2 aluminiums and 3 sulfates to make it equal 6, because now we have 6+ on the aluminium side, 6- on the sulfate side. So that's therefore Al2, SO4 3, not forgetting the brackets as usual. Now, if you don't like the method I just showed you, there is a cheats way of doing it where you don't actually have to understand the chemistry. What you do is you write out the ions as usual. So potassium is in group 1, hence 1+. Oxygen is in group 6, 8 minus 6 is 2, so 2-. And all you have to do here is swap and drop. So literally bring down that invisible 1 to here, that 2 to there, and then rewrite the ions. So your final answer is K2O. And it works with anything really. So let's do aluminium nitrate. Aluminium's in group 3. Nitrate we've learned off by heart from the list above. We're going to swap and drop, so we're going to bring that 3 down, we're going to bring that invisible 1 down, and so it becomes AlNO3, 3, because you brought that 3 down. Let's look at ionic bonding now. So it's ionic, which means it has to be a metal and a non-metal. Use your periodic table to double check that the 2 things you've been given are metals and non-metals. If they're not, they're asking about covalent bonding. So let's have a look at magnesium oxide, for example. Now magnesium has an atomic number of 12 and oxygen has an atomic number of 8. So let's work out their electronic configurations. So 2 electrons go into the first shell, then they fill up to 8. So that's why magnesium is 282 and oxygen is 2.6. We only need to draw the outer electrons here, so don't worry about drawing the whole atom. So there's magnesium's 2 electrons on the outer shell. Here's oxygen's. Make sure you use crosses and dots to distinguish between the 2 atoms. There's 6, so we can clearly see where those 2 electrons will be deposited, and now we can actually draw the answer. So because magnesium's lost its 2 electrons, I'm not going to show any electrons here. Electrons have a minus charge, which is why its net charge will now be 2+, because it's lost 2 electrons. Now oxygen will have gained 2 electrons. Try and draw them a bit more circular than that, that is shocking. And I'm going to use 2 dots to represent the electrons that came from magnesium. Because it's gained 2 electrons, that's why the charge is now 2-. And therefore we can see the formula of magnesium oxide is MgO. Let's look at a different example now, which is magnesium chloride. So magnesium still has an atomic number of 12. Chlorine has an atomic number of 17. So drawing out their electronic configurations again. You can see, to be honest, the outer shell electrons from the group number. So it's up to you which way you do it. So magnesium again, 2 electrons. Chlorine has 7 electrons in its outer shell. So we can see where that first electron is going to go, but there's still a second electron here that needs to go somewhere, which is why we need a second chlorine atom. In terms of your final answer, draw magnesium. It has lost 2 electrons, which is why it's 2+. Chlorine has gained an electron from magnesium, which is why it is 1-. There are 2 chlorine atoms, so that's why I draw a second one, keeping it identical to the first one that I've already drawn. And that's your final answer. Looking now at aluminium oxide, which is the most difficult example. So aluminium has an atomic number of 13, so its electronic configuration is 283. Oxygen has an atomic number of 8, so it's 2.6. So aluminium's outer shell will have 3 electrons on it. Oxygen will have 6 electrons. So we can see where the first 2 electrons will be deposited, which is here. But unfortunately, we've still got a leftover aluminium electron, so we need a second oxygen atom, which I'm going to draw here. You don't need these intermediate steps, by the way, if you can go straight to the answer. I'm just showing you how I found my answer out. So that's where that aluminium's electron is going to go, but that leaves oxygen still missing an electron, because now it only has 7 electrons in its outer shell. So we need a second aluminium atom, still with 3 electrons in its outer shell. So there's one of those electrons, but unfortunately we've still got 2 electrons to give away, which is why we need a third oxygen atom. And finally, it's happy, because you can see where those 2 electrons go. And now let's actually work out what our answer will look like. I hope I've got space for this. Probably won't have. So aluminium has lost 3 electrons, so that's why it's 3+. We need 2 of them, which is why I'm drawing them twice. And then oxygen will therefore look like this. There's 3 of them. Let's label them as oxygen. Let's show their outer electrons. So basically they're clones of each other, they're all the same. And each oxygen gained 2 electrons, which is why their net charge is 2-. So actually the formula of aluminium oxide, as we can see, is Al2O3. Looking at covalent bonding now, we can see we're looking at 2 non-metals. So don't be tempted to draw an ionic bonding diagram. We're going to take a nice straightforward example to begin with, which is water, H2O. So we're going to have a central oxygen atom, 2 hydrogen atoms coming off the side, label the atoms, and then have a look in the periodic table and see how many electrons they have in their outer shell. And remember, that's given by their group number. So hydrogen has 1 electron in its outer shell. Oxygen has 6. 4, 5, 6. And now double check and see that they're both full. Oxygen now has 8 electrons in its outer shell. Hydrogen only has 2, but that's fine because remember the first shell only needs 2 to become full. So that is now a perfectly completed covalent bonding diagram. Let's look at methane now, which is CH4, which you need to know for organic chemistry. So try and arrange this nice and symmetrically. That isn't particularly symmetrical, but it will do. So again, hydrogen has 1 electron in its outer shell, so let's start by filling in those ones. Carbon is in group 4, so it has 4 electrons. And actually that's already done because now hydrogen has 2 in its outer shell. Carbon has 8, so that is now correct. Carbon dioxide is trickier, and I'll show you that example now. So remember that's CO2. Remember with this one that it has double covalent bonds, and that will really help you with your answer. So carbon has 4 electrons in its outer shell, but I'm drawing it like that because I know it's a double covalent bond. Oxygen has 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And they both need to have 8 electrons to be full. So carbon has 8 electrons as 2 shared pairs, and oxygen has 8, so that is correct. The most difficult example you could be given is ethene C2H4. So I'm going to show you how to do that. There's your central carbon atoms. Here's your 4 hydrogens. Label them. It's easiest to start with the hydrogens here, remembering they have 1 electron in the outer shells. Carbon has 4, so let's make sure that hydrogen's happy first of all. So 1, 2, 3, 4. Let's do the other side. 1, 2, 3, 4. And now have a look. Yes, all the hydrogens have 2 electrons in the outer shell, and each carbon now has 8, so that is correct.
Let's now take a look at the chemical structures part of the specification, and when we're talking about chemical structures, we're talking about 4 main structures. That is giant covalent, giant ionic, giant metallic and simple molecular, and you need to know and understand why they have various properties such as either high or low melting points, electrical conductivity, that sort of thing. But we're going to start initially with giant ionic structures. So remember, these are made up of a metal and a non-metal. And what is an ionic bond? Well, it's the electrostatic forces of attraction between oppositely charged ions. So remember that the metal ion is positive and the non-metal ion is negative, and therefore they attract. So why do giant ionic structures have such high melting and boiling points? And that's because they have strong electrostatic forces of attraction between oppositely charged ions. And don't forget to qualify this by saying that they require a lot of energy to break. Why don't they conduct when solid? That's because the ions aren't free to move. Why do they conduct when they're molten or liquid? That's simply because the ions are free to move to carry the current. Why are they brittle? And don't forget that brittle means that they smash easily when hit. That's because when you hit them, or when a force is applied, the layers of ions slide, so the ions with the same charge end up next to each other. So positive charges will therefore repel and the whole structure breaks apart. So that's giant ionic done. Moving on to giant covalent, and we are really looking at carbon here. So we're looking at diamond and graphite, which remember are both forms of carbon. So your definition of an allotrope is different forms of the same element. So why does diamond have such a high melting point? And that's because it has a giant tetrahedral structure, which really means that each carbon atom is bonded to 4 others. So it has many strong covalent bonds, which require a lot of energy to break. Why does graphite have a high melting point? Similar argument, but this time each carbon atom is bonded to 3. You still have many strong covalent bonds and it still requires a lot of energy to break, but because it's bonded to 3 rather than 4 carbon atoms, that's why graphite has a slightly lower melting point than diamond. Why is graphite used as a lubricant? That's because the carbon atoms are arranged in layers with weakened molecular forces between the layers. These require little energy to break, and therefore the layers can slide off each other, hence it's used as a lubricant. Why doesn't diamond conduct electricity? And that's because it has no free electrons. However, graphite does conduct electricity, the reason being that each carbon atom, as we've already said, is only bonded to 3 others, meaning that there's a 4th electron which is free to move and therefore carry the current. A third allotrope we need to know about is C60 fullerene. Now this is really different from diamond and graphite. It's actually a simple molecular structure, which means it has a low melting point, and that's due to weakened molecular forces which do not require a lot of energy to break. It doesn't conduct electricity, and that's because even though each carbon atom is only bonded to 3 others, the 4th electron isn't free to move. It has to stay within that molecule, so it can't carry the current. We should touch on a covalent bond here. Now remember, a covalent bond is a shared pair of electrons. If you want to be more complex about it, you can say it's the electrostatic attraction between the positive nucleus and the shared pair of electrons. Why do simple molecular substances have such low melting points? And that's because they have weakened molecular forces which do not require a lot of energy to break. A small point to note, which is why do simple molecular substances have increasing boiling point with increasing MR? So remember, MR is the relative atomic mass, so it's really saying something like, why does ethane, C2H6, have a higher melting point than methane, CH4? And that's because ethane, so substances with a greater MR, have greater intermolecular forces of attraction between molecules, and these require a lot more energy to break. And remember, when you're boiling these substances, you're not breaking apart the individual atoms from the molecule, you're simply separating one molecule from another. So you're breaking intermolecular forces. Group 1 elements now, so remember that is the first column of the periodic table. It is the alkali metals. They all have the same chemical properties because they have 1 electron in their outer shell. Now remember, as you descend that group, the elements become more reactive. They're all extremely reactive as it is, but as you descend the group they get more reactive. This means that they must be stored in oil because they'll react with the slightest bit of moisture. They're soft and you can actually cut them with a knife, and they oxidize very easily, so they go from being shiny to oxidized very quickly on exposure to air. Other properties they have is they have low melting and boiling points, which makes them quite unusual for metals, and they also have a low density, and we can see this when they're placed in water. They actually float on the water. So again, these are really quite unusual properties for the group 1 metals. Now they're very reactive, as I've already said, and they can react with oxygen to form oxides, so potassium oxide for example. They can react with cold water to form hydroxides, potassium hydroxide for example. They can react with the halogens. Remember, those are the elements in group 7 of the periodic table, to form something like potassium chloride. And they can partake in ionic bonding. Let's now look more closely at observations when they're added to water. So this will be true for all group 1 elements. First of all, they fizz, and what that actually means is they're releasing hydrogen gas. They float, they move around, they form a small ball which eventually dissolves. If you were to add universal indicator to that leftover solution, you would see that it would turn blue, and that makes sense because remember, blue indicates alkali and they're called the alkali metals, so that makes perfect sense. In terms of more specific observations, remember that lithium doesn't produce a flame. However, sodium produces an orange flame when added to water, and potassium produces a lovely lilac flame. Learn the word equations for when they're added to cold water. So I've already touched on this, but a group 1 metal plus cold water will produce a metal hydroxide plus hydrogen, which makes sense due to the fizzing that you witness. So taking lithium, for example, plus water forms lithium hydroxide and hydrogen. We don't add them to steam or to acid because that would be incredibly dangerous. They also burn in air and they produce very characteristic flame colours. So lithium burns to form a red flame, the crimson flame. Potassium again produces a lilac flame, and sodium produces a yellow flame. In terms of making predictions about group 1 metals below potassium, so things like francium. Now you don't need to learn these observations off by heart, but do notice that these observations with water will be more violent because obviously for all the reasons we've already described, the atoms are larger, more shells of electrons, the electron further from the nucleus. So just be prepared to talk about the fact that they'll be more violent, but you'd still see the same set of observations: fizzing, for example, a flame, moving around, floating, melting, etc. Right, so the halogens, we're looking at group 7. So these are the elements including fluorine, chlorine, bromine and iodine. Now don't forget their states at room temperature. Fluorine and chlorine are gases at room temperature. Fluorine is a yellow gas, chlorine is a green gas. Then you have bromine, which is a red-brown liquid, and finally iodine is a grey solid. Don't forget iodine undergoes a process called sublimation, which is when it turns directly from a solid to a gas, and in the case of iodine it goes from a grey solid to a purple vapour. Now the halogens react with hydrogen to form hydrogen halides. For example, hydrogen plus bromine forms hydrogen bromide. These are very acidic and poisonous, and they're also very soluble in water. So something like HCl gas will turn readily into hydrochloric acid, so that's HCl aqueous on addition with water. You need to know about halogen displacement reactions, because more reactive halogens will displace less reactive halogens from their compounds. Let's quickly look at the reactivity of the halogens. So remember, at the top of the group, that's where they're most reactive. Towards the bottom, they're at their least reactive. So if we look at the halogen displacement table, we tend to only look at the elements chlorine, bromine and iodine. You'll find that chlorine displaces both iodine and bromine from their compounds. You clearly don't react chlorine with itself, so potassium chloride, because there'll be no reaction. If you try and displace a potassium chloride, for example, using iodine, that won't happen because iodine is less reactive. So just learn the rules for this and the summary equations. In terms of their general properties, remember they have low boiling points and low melting points, and they are poor conductors of heat and electricity. Moving on to the components of gas in air. So let's look at air. What does it consist of? Well, it's 21% oxygen, 78% nitrogen, 0.9% argon, 0.04% carbon dioxide, and everything else is other noble gases. We might need to look at proving that the percentage of oxygen in air is 21%, and you can use lots of different methods, including the copper method. So in this, what you have is you have two syringes joined by a tube, and in the tube you place copper. Now one of the syringes contains 100 centimeters cubed of air, the other syringe is empty. You heat the copper strongly and you pass the air from one syringe over that copper to the other, and what happens is the copper reacts with the oxygen in the air, forming copper oxide. And then as you repeatedly pass that air over the copper, you will see the syringe alter its volume, and it will go from being 100 centimeters cubed of air to 80 centimeters cubed, or approximately, and that tells you that 20 centimeters cubed contained oxygen, because clearly that reacted with the copper. You can also use iron filings in order to prove that the approximate amount of oxygen in air is 21%. So what you do this time is you get a large glass burette, you place iron filings in it and it's full of air, and you dip the end of the burette into a trough containing water. So the iron reacts with the oxygen in the air, and what you will see happen is that water will move into the burette, and it should move in about 20% of the volume of the burette, which tells you that the air contains 20% oxygen. Looking at various elements reactions in air with oxygen. So first of all, magnesium burns in oxygen and you see a bright white light form, and magnesium reacts with oxygen to form magnesium oxide, which is a white solid. Once you form that magnesium oxide, you can react it with water, and remember magnesium is in group 2, so it is an alkaline earth metal, so if you test that resulting solution with universal indicator, it will turn blue, which is what you would expect because it is alkaline. The reaction taking place now is magnesium oxide plus water forms magnesium hydroxide. Now looking at sulfur's reaction with oxygen, you see a blue flame this time. The poisonous and colourless gas sulfur dioxide is formed. It's a very strong smelling gas. It smells like rotten eggs, in fact. Here is the equation you need to learn, which is sulfur plus oxygen forms sulfur dioxide. If you dissolve that sulfur dioxide in water, you will form sulfurous acid, and make sure you notice its formula. It is different from sulfuric acid's formula. Looking at hydrogen's reactions with oxygen, you see a pale blue flame, water is formed, and your summary equation is hydrogen plus oxygen forms H2O, which is water. Moving on to thermal decomposition now. So what does that actually mean? Well, thermal means to do with heat. Decomposition means breaking down, so it's breaking down a substance using heat, and this is what happens when metal carbonates are heated, they break down. For example, copper carbonate, when heated, it goes from being a green solid, which is copper carbonate, it's broken down to copper oxide, and copper oxide is a black solid. All the carbonates respond quite similarly, so if we had calcium carbonate now, we heated it, it would break down to calcium oxide and carbon dioxide. Although this might seem slightly out of joint, we now need to look at the effect of excess carbon dioxide on the environment. So remember, carbon dioxide is a greenhouse gas. So enhanced greenhouse gases, so more CO2 being released, will lead to global warming. Now global warming causes polar ice caps to melt. Because they've melted, it means that there is a rise in sea level which floods low-lying land. This obviously causes the destruction of many habitats. It can cause the extinction of species that get caught up in it. And other effects include changes in bird migration patterns, so that's where they fly in the summer and the winter, and also increased extreme weather. The reactivity series, so you need to learn the order of metals in the reactivity series, and that is potassium, sodium, lithium, calcium, magnesium, aluminium. Then we mention carbon, because although it isn't a metal, it's good to use it as a reference point. This is followed by zinc and then iron. Hydrogen comes next, not a metal, but still a good reference point. And lastly, our unreactive metals go copper, silver, and then lastly, the most unreactive is gold. And that explains why you find silver and gold native in the Earth's crust. You can literally just find it in streams and rivers, and that's because it's incredibly unreactive. Even though aluminium looks fairly reactive because it appears quite high in the reactivity series, due to its oxide layer, it means it's less reactive than you would imagine. So we have an unknown metal and we don't know how reactive it is, so there are several things we can do to try and determine its position in the reactivity series. So first of all, we would try to react it with cold water. Now only very reactive metals, such as those found in group 1, so we're looking at potassium, sodium and lithium for example, will react with cold water, and they'll form metal hydroxide plus hydrogen, which we've already met. If they don't react with cold water, you can then try steam, and this will produce a metal oxide and hydrogen. And then lastly, if it doesn't react with steam, you can try acid, and that will produce a salt plus hydrogen. And you obviously wouldn't try reacting group 1 metals with acids because they are far too reactive. Do notice that when you look at the reactivity series, only elements which are more reactive than hydrogen will react with acids, and that's because acids contain hydrogen, such as hydrochloric acid, it's HCl, sulfuric acid, H2SO4, nitric acid, HNO3. So in order to react with acids, they must be more reactive than hydrogen. Looking at protecting iron from rusting. So rusting is when metals flake away, and you only use the word rust when you're talking about iron. If you talk about any other metal, you can't call it rust, you have to say it corrodes. So you could say that zinc corrodes, but only iron rusts. So what conditions are needed for rusting to occur? You need water and oxygen for this, and salt actually increases the rusting process but is not necessary. What are the different ways in which we can prevent rusting? There are the simplest ways, which is just simply painting or using oil and grease to protect the iron and stop it being exposed to water and oxygen, or you can become more fancy and use methods such as galvanizing. So galvanizing is when you use a more reactive metal such as zinc, and it reacts before the iron. And so actually what happens is the zinc ions and donates electrons, and what that means is the electrons can flow to iron, and therefore if the iron starts to rust and form ions, this is hard, why have they got the same name? Those electrons which have been donated from zinc can help the iron form its iron atoms again so it doesn't rust away. Try not to worry too much if you're not understanding what I'm saying, just learn that galvanizing is using a more reactive metal to protect iron. When other metals oxidize and react in preference to the iron through the method of galvanizing, don't forget we call this sacrificial protection. And because we've just talked about the transfer of electrons, let's remind ourselves of the definitions of oxidation and reduction. So oil rig, oxidation is the loss of electrons and reduction is the gain of electrons. Redox now, and that, as the name suggests, is a reaction where reduction and oxidation occur at the same time. A reducing agent is a substance which causes another substance to be reduced, so it forces the other substance to gain electrons, and therefore, by definition, a reducing agent is therefore oxidized. An oxidizing agent causes a substance to become oxidized, so it forces the other substance to lose electrons, and therefore, by definition, an oxidizing agent is reduced. Indicators. So you need to learn various colours of indicator. So obviously the most common one is universal indicator. That shows the pH scale from 0 to 14. Remember, 0 to 6 is acidic, 8 to 14 is alkali, so 7 is neutral. Universal indicator in a neutral solution is green, in an alkaline solution is purple, and in an acidic solution, if it's a strong acid, will be red, and that will be about pH 1. Other indicators you may come across have less of a range of colours, such as methyl orange. Now methyl orange is red in acid, it is yellow in alkali. Phenolphthalein, which is a very difficult word to spell, is colourless in acid, and it is a beautiful pink colour in alkali. And lastly, litmus is red in acid and blue in alkali. So what makes something an acid? Well, it's the fact it can donate hydrogen ions. And what makes something alkali? It's the fact that it can donate hydroxide ions. We're now going to cover the salts topic, and when we're talking about salts we need to know a lot about acids and bases because that's where the salt originates from. So do remember your definition of an acid, which is that it is a H+ donor. A base is a H+ acceptor, and it also tends to be a hydroxide donor. And examples of bases include metal carbonates, metal hydroxides and metal oxides. Just remember the difference between a base and an alkali. They're very similar. An alkali is simply a soluble base. So remember, all alkalis are bases, but not all bases are alkalis. So some background about salts. So effectively, a salt is formed when the hydrogen of an acid is replaced with either metal or ammonium. For example, say you had hydrochloric acid, you acted it with potassium oxide, then you would end up with potassium chloride, which is the salt. Taking sulfuric acid now, pretend we reacted it with calcium carbonate, you'd end up with calcium sulfate, which is the salt. So now let's look at some common acids and the salts that they produce. Now, in terms of the reactivity of acids, remember that only metals above hydrogen in the reactivity series will react with acids. So things like copper, silver and gold, which lie beneath hydrogen in the reactivity series, will not react. Elements at the very top of the reactivity series, such as potassium, sodium and lithium, they will react extremely explosively, and I don't recommend that anyone tries this because it would be extremely dangerous. So now let's take you through the salt equations. So we're going to start with looking at the general equation. When you have metal plus an acid, that forms salt plus hydrogen, and I'm going to show you some examples. If you have metal oxide plus an acid, then you make salt and water. Metal hydroxide this time, it's the same as metal oxide in that you produce a salt and water. And lastly, metal carbonates. When you react those with acids, you produce a salt plus water, and then because of the carbonate, you produce carbon dioxide. So do make sure that whatever is on the product side started off on the reactant side. Don't start creating carbon dioxide on the right-hand side when there was no carbon on the left-hand side. And similarly, don't have hydrogen and water forming on the right-hand side. Only one of them forms, so make sure you know which one it is. Solubility rules, learning which salts are soluble and which are insoluble. The reason why I'm smiling is because this is disgusting. It's awful, I really struggle to remember them. Now there is a huge table which you can try and learn off by heart, but I much prefer to learn the rules, and if you assume that most things are soluble and learn the exceptions, that's a good way to go. So let's start by stating that all nitrates are soluble. All potassium, ammonium and sodium compounds are soluble. All sulfates are soluble. There are 3 exceptions, and that is lead-2, calcium and barium sulfate. All chlorides are soluble except from lead-2 chloride, and silver chloride. Now we switch and we look at things which are insoluble. So we say that all carbonates are insoluble. The exceptions will clearly be the sodium, potassium and ammonium compounds, which makes sense because I've already told you that the sodium, ammonium and potassium compounds are soluble. And similarly, all hydroxides are insoluble, the exception being sodium, potassium and ammonium compounds. So let's just do a quick test on that. So I'm just going to say a couple of salts and you need to decide if they're insoluble or soluble. So starting with lead nitrate, that is soluble because it contains nitrates. Next up, potassium carbonate, that is also soluble because it contains potassium. Now we're looking at magnesium sulfate, that is soluble because remember all sulfates are soluble with a few exceptions. What about barium sulfate? Well, that was one of the exceptions you had to learn, so that is insoluble. And now calcium carbonate, that is insoluble because it is carbonate and it is not sodium, potassium or ammonium. So I hope you can see you can work it out using these rules. So let's look at the different methods for making these salts, and we're going to start by looking at soluble salts, but do notice these are ones which do not contain ammonium, potassium or sodium. So what you can do here is you can use metal oxide, a metal hydroxide or metal carbonate. You react it with the acid and you form your soluble salt. You can also use metals plus acid, so it doesn't need to be combined with an oxide, hydroxide or carbonate, but do notice that you need a metal which isn't mega reactive, because clearly if you're reacting it with an acid you could end up with a dangerous explosion if you're using group 1 metals, so be sensible and use something like magnesium. Now the method you're going to actually use is crystallization. Your summary for this is that you're going to react, for example, your metal hydroxide with your acid. You're going to filter in order to remove any undissolved solid. Then you're going to evaporate, so you're going to place that solution in an evaporating basin over a Bunsen burner with gauze and a tripod, and you're going to get rid of excess water, so you'll evaporate some of the water. Then you're going to allow the mixture to cool, and eventually you want to let it dry out in a warm place, so on a warm windowsill, in a drying oven for example, or on paper. Getting even more detailed now, we need to look at the Bronsted-Lowry theory of acids. Don't worry too much about this. They were extremely specific over their definitions of acids and bases. They really only wanted you to use hydrogen ions when defining them. So a Bronsted-Lowry acid therefore is a hydrogen ion donor, which is fine because we already know that. A Bronsted-Lowry base is a hydrogen ion acceptor, so don't mention anything to do with hydroxide ions when you're talking about Bronsted-Lowry. Let's look at an example of the Bronsted-Lowry theory in action. So we're going to use the dissolving of hydrogen chloride in water. So we've got H2O and HCl, and it's a gas at this point, so notice that. When they are reacted, what you find is a hydroxonium ion is formed, which is H3O+, and a chloride ion, which is aqueous. So we have water reacting with hydrogen chloride, forming the hydroxonium ion H3O+, plus the chloride ion. So let's try and work out which species are acting as Bronsted-Lowry acids and bases. So clearly, the hydrogen chloride is acting as a Bronsted-Lowry acid because it donates a hydrogen ion, and the water acts as a Bronsted-Lowry base because it has accepted that hydrogen ion to become the hydroxonium ion H3O+. Oh, we can move away from that disgusting topic now and just look at generic tests. So the test for hydrogen, don't say it's the squeaky pop test, you won't get a mark for that. You need to say that you hold a lighted splint over the gas, and if hydrogen is present there should be a squeaky pop. With oxygen you need to say that it relights a glowing splint. Carbon dioxide, remember, turns lime water cloudy. Chlorine bleaches damp litmus paper. And ammonia turns damp red litmus paper blue. Now I've given you the most concise, precise definitions for this, so make sure you've learnt them. Every single word matters here. So for example, damp is worth a mark, red litmus paper worth a mark, so make sure you learn them properly. And now we're getting more complex and we're going to look at flame tests. So remember, if we have an unknown metal ion, a flame test is a good way of working out what that metal was. So in terms of carrying out a flame test, remember that you're going to use a clean nichrome wire, which is, you could clean it using hydrochloric acid, but the point is you don't want any contaminants on the end of that nichrome wire. Then you dip it in the sample to be tested and then hold it in a roaring blue flame, and that is key. You can't be adding it to a yellow sooty flame, that won't work because the yellow will obstruct the colour, so hold it in a roaring blue flame. So the colours. Now if we've got lithium ions, you will see a lovely red crimson colour. Sodium, you'll see a yellow flame, and potassium, as with when you add it to cold water, you will see a lilac flame. Calcium goes an orange-red colour or a brick red colour, and copper goes a blue-green colour. If you don't want to carry out a flame test, you can use a precipitation reaction, and you can look at the colour precipitate formed once you've added sodium hydroxide. So if you add sodium hydroxide to something containing copper, you will see a blue precipitate formed. Iron 2 will form a green precipitate, and iron 3 will be a brown precipitate, and I remember those because they're kind of muddy, earthy colours, so it goes green for iron 2, brown for iron 3. Testing for ammonium ions now, which is NH4+, again add sodium hydroxide. You won't see a precipitate form in this case. Instead, a stinky gas will be released, which should be ammonia, and you test for the presence of that ammonia using the method I've already described, which is that it should turn damp red litmus paper blue. Okay, moving over now to test for negative ions. We've looked at metal ions and ammonium, so we're looking now at the halides, which is group 7, the halogens. So first of all, you need to add nitric acid. You add that dilute nitric acid in order to remove any carbonate ions which might interfere with your test. Following that, you add silver nitrate, and then you'll end up with a range of precipitates. So looking at the chlorides, if you add chloride ions to silver nitrate, you produce silver chloride, which is a white precipitate. If you add silver nitrate to something containing bromide ions, you make silver bromide, which is a cream precipitate. And lastly, adding silver nitrate to something containing iodide ions will produce a yellow precipitate. So notice those colours get darker. We go from white to cream to yellow. And be prepared to write the ionic equation for this, which will be, for example, with chlorine, it will be Ag plus Cl minus forms AgCl solid. Now we need to look at the chemical and physical tests for water. So the physical test for water is you just need to check a substance's boiling point. If it boils at 100 degrees Celsius, you know you have water. And linked with this, how do you show that water is pure? Well, I've already talked about pure substances having one distinct boiling point, and the same is the case with pure water. The whole lot should boil at 100 degrees. If it's boiling over a range, it tells you it's not pure. Now, using a chemical test for water, you want to add white anhydrous copper sulfate. Anhydrous means lacking in water. Once it's exposed to water, it should turn blue, and that tells you that the substance you have is water.
So I thought the easiest way to talk you through the energetics topic was to take you through some past exam questions, because they're pretty much all the same. So the moment you see a polystyrene cup and a thermometer, we're looking at enthalpy. So be aware of what endothermic and exothermic means here. So remember, exothermic means gives out heat energy, and endothermic means takes in heat energy. And with an exothermic reaction, you're looking for a negative delta H, whereas endothermic, you're looking for a positive delta H. Again, in terms of the actual temperature of the beaker or the cup, an exothermic reaction will get hot and an endothermic one will get cold. And if you bear that in mind, hopefully it'll make answering these questions far more straightforward. A student uses this apparatus to investigate the heat energy released when nitric acid is added to potassium hydroxide solution. So we've got nitric acid inside the burette, which is going to be dripped into the polystyrene cup containing potassium hydroxide. She uses this method. Put 25 centimeters cubed of potassium hydroxide solution into the polystyrene cup. Measure the temperature of the potassium hydroxide solution. Add 5 centimeters cubed of nitric acid from the burette. Stir the mixture and measure the highest temperature reached. Add further 5 centimeters cubed samples of nitric acid. Stir and measure the highest temperature reached after each addition. Name the piece of apparatus that should be used to measure the 25 centimeters cubed of potassium hydroxide solution. So you need a fairly precise piece of apparatus here, which is why you should state either a pipette or a burette. Measuring cylinder would not be precise enough. The table shows the student's results. So here she's got the different volumes of acid and the highest temperature reached, and we can see the highest temperature was reached when the largest volume, 30 centimeters cubed of acid, was added. The result for 20 centimeters cubed is anomalous. Suggest two possible mistakes other than misreading the thermometer. that the student might have made to produce this anomalous result. So remember, anomalous means that it's the odd one out. It isn't quite what you would expect. And if we actually look at those results, it's 31, which is pretty close to 29. So we're thinking that the temperature is too low. So what could have caused the temperature to be too low, aside from misreading the thermometer? Well, first of all, she could have added less than 5 centimeters cubed extra of the acid. Secondly, she might not have waited until the highest temperature was reached. And thirdly, remember, when you're doing this experiment, it's really important that you stir the reactants. So she might not have stirred them properly. Suggest a true value for the temperature when 20 centimeters cubed of acid is added. So let's have a look. You kind of want somewhere that sits between 29 and 37. So I'd probably go in at 33. In another experiment, the student records these results. Volume of potassium hydroxide solution, starting temperature of potassium hydroxide solution, total volume of acid added, and the highest temperature reached by the mixture. And we're calculating the heat energy released using this equation, Q equals mc delta T. So this is really nice. They've given us pretty much all of it. So Q is what we're after. Mass of the mixture, so you need to add those two volumes together. So 25 plus 25 is 50. Times the specific heat capacity, which we've been given, is 4.18, times the temperature change, which is, we know it goes from 16 to 35, meaning that there has been a 19-degree increase. And then when you pop that into your calculator, you get a value which is 3970 to 4 significant figures. 3. An excess of zinc powder 5 grams was added to 50 centimeters cubed of 0.5 mol dm to -3 copper sulfate solution in a glass beaker. The initial and final temperatures are shown on the thermometers below. Use the picture of the thermometers to complete the temperature before and the temperature after, as well as the temperature change. So this is about accurately reading the thermometer. So before, you can see that it is 18.7 degrees Celsius. The temperature after is 25.3 degrees Celsius, which means the temperature change, once you pop that into your calculator, is 6.6 degrees Celsius. Calculate the energy change Q which occurred during this experiment. So remember, we're using Q equals mc delta T. The mass is the actual mass of the liquids which have been added, not the solid. So ignore the 5 grams. If you look here, it's here, 50 centimeters cubed, which is why the mass is 50. We're going to times our specific heat capacity, which is 4.18, and that's always true. And then times the temperature change, which I've just calculated, is 6.6. And once you pop that into your calculator, you get a value which is Q is 1379.4 joules. And then hence calculate the enthalpy change delta H of this reaction. So use this equation, which is delta H equals Q over N. So we need to work out the number of moles. So number of moles is concentration times volume. So look up here again. Our concentration is 0.5. Our volume is 50, which we need to divide by 1,000 to make sure that it's in dm cubed rather than centimeters cubed, which is therefore 0.025. And then lastly, make sure that Q is in the correct units. So we need it to be kJ. So what we do is we take this number here and we simply divide it by 1,000 to get 1.3794, and then just pop those numbers in. So 1.3794 divided by 0.025, I'm always running out of space. And you get a value which is 55.2 kJ mole. Now do have a look at the thermometers now and make sure you're happy that the temperature went up. Yes, it did, because it went from being 18.7 degrees Celsius to 25.3. It's got hot, which means it's an exothermic reaction, which means our delta H here is positive, and don't forget that for the last mark. By the way, that was a lot of maths, especially that number of moles equals concentration times volume. That's very much to do with the titrations topic. So have a look at that part of the video if you don't understand why I did the numbering, why I did the calculation like I did. So suggest the biggest source of error in this experiment and how the procedure used could be modified to decrease this error. Well, it's always going to be heat loss to the surroundings. So rather than using a glass beaker, you could use a polystyrene cup with a lid, because that is a better insulator.
Now we're moving on to rates of reaction. So looking at the effect of temperature, surface area and concentration on rates of reaction. So what effect does increasing the temperature have on the rate of reaction? Well, clearly it's going to increase it. The reason why is because particles have greater kinetic energy, so they collide more frequently. The collisions are harder, and therefore a greater proportion of these collisions result in the required energy to overcome the activation energy. Looking at concentration now. So if you increase the concentration of particles, that means that there are more particles in the same volume. Clearly, collisions will occur more frequently, and therefore the rate of reaction will increase. Surface area now. If you increase the surface area, for example by powdering marble chips, powdered marble chips have a larger surface area than giant lumps. And so by increasing the surface area, you're ensuring that you have an increased frequency of collisions, and therefore the rate of reaction will increase. And do make sure you can argue this from if you decrease the surface area, decrease the concentration and decrease the temperature. You just need to say the exact opposite. Remember, there are several ways in which you can measure the rates of reaction. So rates of reaction are given by, for example, a change in volume over time, a change in concentration over time. Now, if we use the marble chip example, remember that marble chips, when reacted with hydrochloric acid, they will produce carbon dioxide. So you can measure how quickly that carbon dioxide is produced, either using a top-pan balance. Now remember, that needs a high resolution because carbon dioxide doesn't weigh very much, so you need at least like 0.00 on your weighing scale in order to measure that difference. So when it escapes out the top of a conical flask, you'll see the mass decreasing, and you can measure that over time. Equally, you could use gas syringes, and that will show you the volume of carbon dioxide that's released. You can't use this method if you're measuring hydrogen gas because it is too light, so you won't actually be able to see a change in the reading on the measuring balance. Sometimes there are experiments involving crosses being obscured due to a precipitate being formed, so you measure the time taken for the cross to disappear, but that's obviously fraught with difficulties because it's very much human judgment as to decide when that cross disappeared. So do be prepared to talk about some limitations related to the methods used. Now we're looking at Equilibria. I'm very excited, I'm getting near the end of this, and it's been going really well, so I'm happy. So with the term exothermic, let's define it. First of all, it means the release of heat energy. So looking at endothermic reactions, you'll see the opposite. So heat energy in this case is taken in. So chemical equilibria now, we are looking at reversible reactions here. So be aware of this special arrow. This is your reversible arrow, and it tells you that the reaction is happening in both the forward and backwards direction. And what that really means is the reactants react to produce the products, as we're used to seeing, but then the products will fall apart effectively and produce the reactants again. So these aren't ideal conditions when we're talking about industrial processes, because it basically means you make very little of the product that you're after, and we use the word yield to describe the amount of product produced. A summary now of what happens when we choose to alter reaction conditions. So remember, we can alter the position of equilibria if we change both the temperature and pressure. Remember, when a reaction is exothermic, the whole reaction gets hotter, and when it is endothermic, the whole reaction gets cooler. So if we start by increasing the temperature, we know we need to oppose the change, so we're going to favour the reaction, which results in a decrease in temperature, which is why increasing the temperature favours the endothermic reaction. And that means that the position of equilibrium will shift to favour that endothermic reaction. So if you have an equation and the delta H says that it is positive, we know that the forward reaction is therefore endothermic. So increasing the temperature will favour the forward reaction. Decreasing the temperature will favour the exothermic reaction, and the position of equilibrium will shift to favour that. Let's look at another example now. So I'm going to bring up an equation which is showing NO2, reversible arrow, and N2O4, and do notice their colours. NO2 is brown and N2O4 is colourless, and look at the delta H sign, it is an exothermic reaction. So let's see what happens when we increase the temperature. So what happens when we increase the temperature is the endothermic reaction will be favoured, which means the reverse reaction will be favoured. So the position of equilibrium shifts to the left. You therefore make more NO2, and so therefore the colour changes and it becomes brown. So let's look at organic chemistry, one of my favourite topics. So first of all, organic chemistry, what are we talking about? We're talking about hydrocarbons. So what is a hydrocarbon? It's a compound containing hydrogen and carbon only. Make sure you say only in order to get that second mark. So when we're looking at organic chemistry, we're really looking at different families of compounds, and the simplest family is the alkanes. And I'm going to show you now how to draw out the first 4 alkanes, and we'll have a look at their general formula.
Let's look at how we're going to draw various families of compounds, starting with the simplest, which is the alkane family. Do notice their general formula is CnH2n plus 2, and you must obey that when you're working out the molecular formula. If we take C4H10 as an example, this is a molecular formula because it shows the actual atoms of each element present in the compound. So it shows that this particular compound has 4 carbon atoms and 10 hydrogens. To make it into an empirical formula, just cancel down those numbers. So it becomes C2H5, because you can obviously divide 4 and 10 both by 2. This is therefore the empirical formula because it shows the actual atoms of each element present in a compound. And then just to notice, a displayed formula is when you draw out all the bonds, so something like that. So let's start by working out the first alkane. So obviously it's going to have 1 carbon atom. According to the general formula CnH2n plus 2, so substitute in the number of carbon atoms as n, so it becomes C1, and then 2 times 1 is 2, plus 2 is 4, so H4. Because it looks a bit strange to write the 1, I'm just going to erase that. There's an invisible one, so it's CH4. Its displayed formula looks like this, which is you draw the carbon in the middle and hydrogens around the outside, remembering that each carbon atom forms 4 bonds, each hydrogen forms 1 bond, and you must remember that to help you draw them. Its name, well, it contains 1 carbon, which is why it's meth, and it's an alkane, which is why it's methane. So looking at the second one this time, 2 carbons, so we're going to have C2, and then according to the general formula, 2 times 2 is 4, plus 2 is 6, so its molecular formula is C2H6. Drawing it out, therefore, carbons in the middle, then you've got your hydrogens filling up around the edge, each having 1 bond, and each carbon atom has 4. Because it's still an alkane, it ends in ane, but it contains 2 carbons, which is why it's ethane. The third one now, so it's C3, 2 times 3 is 6, plus 2 is 8, H8, 3 carbons in a line. Ends in ane, it contains 3 carbons, so it's propane. For 4 carbons I ran out of space, so it will be C4H10, and it contains 4 carbons, which is why it's bute, still an alkane, so butane.
So these are the simplest hydrocarbons, and we call them saturated, and that's because all the carbon bonds are single. If we look at alkenes, they are unsaturated, and that means they contain a double carbon bond. I'm going to show you how to draw the first 4 alkenes.
Let's now look at the alkenes, and remember they have a general formula, which is CnH2n. Let's first of all start by discussing the functional group of the alkenes. Remember, this is the series of atoms or bonds which makes a particular family of compounds special. So here we see that the alkenes contain a C double bond C. By definition, therefore, they need a minimum of 2 carbon atoms to exist, which is why one carbon alkene does not exist. And we have to start with the 2 carbon. So starting with the 2 carbon one, we know we need to substitute 2 in as the n, so it becomes C2 and then simply H4. The displayed formula, we need a double bond, and therefore we're going to fill up our hydrogens. Do notice again that the carbons have 4 bonds, the hydrogen has 1, contains 2 carbon atoms, which is why it begins with eth. It's an alkene, so it's ethene. Looking at 3 carbon atoms now, so C3H6. Again, make sure you're filling these up properly, double checking the bonds. I can't reiterate this enough. And this will be 3 carbons, so prop, it's an alkene, so propene. Now looking at the 4 carbons, which is when it gets a bit more interesting. So we've got C4H8, and therefore we can draw the first version of this like this. In terms of its name, it's butene. However, We now need to look at the other available isomer. Remember then, isomer is something with the same molecular formula but different structural formula. So if we draw that molecular formula out again, C4H8, but we try and work out a different structural formula, we can simply shift that double bond along so it now appears in the middle, and now just fill in those hydrogens, making sure you don't draw too many bonds on those central carbons. And you can see this is still C4H8, however the structures are different, and therefore these are both isomers, and the way in which we name them is according to where you find that double bond. Because the double bond in the black version is between the first and second carbon, we call it but-1-ene. Because the double bond is between the second and third carbon atom, we call this but-2-ene. So let's try and work out the various isomers we can draw for C5H12, which is obviously pentane. So let's start by drawing the straight chain isomer straight away, because that's the easiest to do. Because we're drawing isomers, it's likely we need to draw a branched version now, so I'm going to add a methyl group. It needs to be on a minimum of the second carbon along, because if you draw it on the first one, it's just like a straight chain isomer, but just going around the corner. You need to ask your chemistry teacher if you don't quite know what I'm talking about there. And make sure we've got 5 carbons, so I've drawn 4. Here's the 5th. Then fill up with hydrogens. And just double check them. So we've definitely got 5 carbons. I've got 3, 6, 7, 8, 9, 10, 11, 12. Yep, so that's C5H12. Let's work out its name. Well, the longest chain is but, is 4 carbons. We've got a methyl group on the second one, which is why it's 2-methyl butane. Try not to capitalise that B, I shouldn't have done that. And then let's work out where the next isomer will be. Well, we can't go and add the methyl group onto this carbon instead, because that would actually be the same isomer as the one I've just drawn, because it's still on the second carbon, but just looking right to left. So I'm just going to have to add another methyl group, I think, off that second carbon, which will look like this. And I do have 1, 2, 3, 5 carbons, so that's right. Just fill up the hydrogens and count them all up. So 5 carbons, 3, 6, 9, 12. Yep, that is correct. Right, this is going to be more difficult to name. So the longest carbon chain has 3 carbons in it, which is why it's propane. It's propane, pane rather than ene, because it's an alkane. There's no double carbon bonds. And we've got 2 methyl groups, and they're both off the second carbon, which is why it's 2, 2. There's 2 of them, so it's di, and then methyl group, so it's 2, 2 dimethylpropane.
Now, these families of compounds we call homologous series, and that's just a fancy way of describing a family of compounds. So what can we say that all members of the same homologous series have in common? So what do all alkanes have in common? What do all alkenes have in common? Well, first of all, they have the same chemical properties, which makes sense. They're going to react in a similar way because they have the same functional group. They're therefore going to have the same functional group, which is good because I just said that. They obey the same general formula. So all alkanes, for example, will follow CnH2n plus 2, whereas all alkenes will obey CnH2n. And then they show a trend or a gradual change in physical properties, which again makes sense. So ethane has 2 carbon atoms, whereas methane has 1. So therefore you'd expect ethane to have a higher melting point and boiling point, which it does. So what is a functional group? Well, it is an atom or a group of atoms which determine the chemical properties of a compound. So we talked about alkanes and alkenes, but where do they all come from? And they come from crude oil, which is a black sticky substance which comes out of the Earth's crust, and it has made some people billionaires because this stuff is worth a lot. Why? Because once it has been sorted, once it has gone through fractional distillation and been separated out into various fuels, that can be sold for a huge amount of money. Why? Because fuels are essential for how we run our lives, it's how we heat our homes and how we run our cars. So what is a fuel? Well, it's a substance which releases energy when burnt. We've talked about crude oil, but how is fractional distillation actually carried out? So we get our crude oil, which we know is a mixture of hydrocarbons. We heat it until it evaporates, and then we pass that vapour into a fractionating column or tower. Now that fractionating column has a temperature gradient, which means it's hotter at the bottom and cooler at the top. So in terms of these various crude oil fractions, and a fraction is just a group of compounds with similar boiling points, they will condense at different positions within the fractionating tower. So the longer chains will condense at the bottom where it is hottest. So just make sure you learn my summary if you're not following what I'm saying, because you'll get all the marks anyway. Now looking at the top then, which we need to go through the order in which the fractions are condensed. So refinery gases occur at the top. After that you have petrol, then you have kerosene, followed by diesel, fuel oil, and lastly bitumen. So what are the various uses of these different fractions? Well, refinery gases are bottled gas which we use in our central heating. Petroleum, or gasoline as it's otherwise known as in America, is obviously used as a fuel for cars. You have kerosene, which is a fuel for aeroplanes. Diesel is a fuel for lorries and buses, so anything big. Fuel oil is used as ship fuel. And lastly, bitumen is used for road surfacing or roof material. I don't know if that's a verb or not, to be honest, but I think it's used to help stick down roofs. I have no idea. A couple of words to be aware of. First of all, viscosity. So that's how readily a fluid flows. Be aware that the more viscous a fluid is, the less readily it flows. So honey is very viscous because it's slow to flow. I like the fact that that rhymed. And water is very unviscous or not viscous at all because it runs very quickly. Flammability, obviously that's to do with how readily something sets alight. Volatility is how readily something turns into a gas. So if we take the various fractions and we make a few comparisons, let's compare the viscosity, volatility and boiling points of bitumen compared with refinery gases. So clearly bitumen will be more viscous, it will be less volatile, and it will have a higher boiling point. It will also have a darker colour because it's a brownish sticky colour, whereas refinery gases are colourless. So do be aware and do be willing to make comparisons and make full comparisons. So say refinery gases are lighter in colour, have a lower boiling point, are less viscous, etc. So once we've got these fuels, what do we need to do to them? We need to burn them, and that's where complete and incomplete combustion takes place. So complete combustion is when you burn something in a plentiful supply of oxygen. And that means you produce carbon dioxide and water as a byproduct, which is a good thing because neither of these things are toxic, although there are obvious environmental issues with carbon dioxide production due to it being a greenhouse gas. Incomplete combustion is when you have insufficient oxygen, and that means you don't produce carbon dioxide. This time you produce carbon monoxide and water. So what are the issues relating to carbon monoxide? Well, it is extremely toxic and poisonous, and that's because it combines with the hemoglobin in red blood cells, forming carboxyhemoglobin, and that means that red blood cells can no longer transport oxygen around the body. Acid rain now, so we're looking at more environmental issues. So acid rain comes from two areas. Firstly, nitrogen and oxygen in car engines reacts due to the high temperatures found, forming nitrogen oxide. That reacts with water in the atmosphere, forming nitric acid. So there's your first acid rain. Next, crude oil can contain sulfur impurities, and when burnt they form sulfur oxides. That reacts with water, forming sulfuric acid. So there's your second acid rain. And acid rain gets into lakes and rivers, making them too acidic, therefore killing aquatic animals. It damages trees and it damages limestone buildings, and you must mention that they're limestone. Cracking now, remember that is a process carried out in order to break large hydrocarbon chains into smaller, more useful ones, and it's all due to demand because effectively the shorter chain hydrocarbons, the shorter chain alkanes and alkenes make much better fuels than the long chains, which is why we carry out cracking. Do remember that you need a high temperature, which is between 600 and 700 degrees Celsius, and you need an alumina or silica catalyst in order to speed up the process. Let's touch on a few reactions that you need to be aware of. So if we take an unsaturated hydrocarbon, so an alkene, and we react it with bromine water, now you must remember the colour change. What you'll see is it will go from being orange to colourless, and I'll show you the summary equation now.
I could ask you, what is the test for an alkene or an unsaturated hydrocarbon? That's actually the same question. So effectively you're testing for the presence of the C double bond C. What you'd write as your answer is that you add bromine water, and in terms of your observations, what you would see is that it would go from orange to colourless. Let's actually look at an example. So we'll take ethene. We're adding bromine water. Remember, bromine is diatomic, hence why I'm saying Br2. And then what happens is the double bond breaks, meaning that there are two available spaces for bromine to join on, which is here and here. And there's no byproduct because of that. And because bromine simply added itself, you say that this is an addition reaction. So what is the type of reaction? Addition. You add bromine water and it turns from orange to colourless. Now looking at alkanes reactions with bromine water. So alkanes, or a saturated compound, it's basically the same thing. What you see this time, I'm going to take methane as my example, but I could have used ethane or propane. We add it to bromine water. But what happens this time is one of the hydrogen pops off, the bromine joins, you complete the rest of the molecule, and what you have left over is clearly a hydrogen that's just left methane and another bromine atom, which is why this is your equation here. Because all that's happened is that hydrogen has simply been swapped or substituted for bromine, we say that this is a substitution reaction. So you can actually see what's happened here. Now we're going to look at addition polymerization. And they could ask you to show this as an equation. So I'm going to show you what's going to happen. We are taking a monomer, such as ethene. Got to make sure I pronounce that properly, ethene. This is your monomer, which means it is a small subunit. Because it is an addition reaction, we're effectively going to add lots of them together, which is why we write an N here. That just means you have lots of them. Then we need to draw some big square brackets. You want to break that double bond, as I've done there, extend the bonds, and now just complete the rest of the structure. And you write an N here to show that there's lots of them, and this is the polymer formed. And if you were to name them, we know that that was ethene. Because there's many of them joining together, we say that the polymer formed is polyethene, which you've probably heard of before and not realised it's polythene. And that's used to make cling film and plastic bags, etc. Let's take propene now, and I'm going to draw propene like this just to make it easier to draw the polymer. But I hope you can see that that is propene, it is C3H6. Again, that's our monomer. We're going to have any number of them, hence the N. Big square brackets, break that double bond, and now just complete the atom. Be very careful where you draw your bonds, make sure those carbons are joining. Extend the bonds out, draw your N, and this is therefore polypropene. This is a harder plastic than polyethylene, so it's used to make buckets, windows, etc. Let's take a third example now. Again, square brackets, break that double bond, extend the bonds, and then just complete. And this is polytetrafluorine.
What does biodegradable mean? It means breaking down a substance using microorganisms, and everything these days we want it to be biodegradable. We don't want plastics hanging around for hundreds of years, which is why it's really good if they say that they're biodegradable. What problems are associated with the disposal of addition polymers, so really problems associated with plastics? That is that most of them are non-biodegradable. They are unreactive, which means it's difficult to break them down. And when you burn them, as a different way of disposing of them, they produce lots of toxic gases. So there's no one good way of disposing of addition polymers or plastics, because they just fill up your landfills, they don't rot, they don't biodegrade, they're unreactive, and when they're burnt, they give off nasty toxic gases. Do notice that biopolyesters are biodegradable. Thank you so much for watching my video. Well done if you made it to the end. Don't forget you can buy my Science with Hazel Perfect Answer revision guides on my website. They're available right now at www.sciencewithhazel.co.uk.